have here Ozsváth from Princeton for the annual Zabrodsky Lectures in Homology and Geometry. And we're talking about not Floer homology and grid diagrams.
Great, well thank you for having me again, and thank you for coming to the second lecture. So I'm going to talk about, last time I talked about an invariant for knots and talked about its properties, and today I'm going to give a definition of it. This is not the first definition, but this is certainly the easiest definition to talk about. Okay, so I even have notes, so I'm going to hold my notebook. Okay, so I'm going to give a definition of what I called not Floer homology last time, and today I'm going to call it grid homology because that's one of the definitions. So the material I'll talk about was really first found in a paper of Manolescu, myself, and Sarkar, and further developed by Manolescu, myself, Zoltan Szabo, and Dylan Thurston. And it's also the topic of our book of myself, Stipschitz. So this was from 2006. And Szabo, we wrote a book about this, which just appeared. It's too expensive.
It's in the library.
It's in the library. Okay. You should negotiate before you sign book contracts to make sure that your books are cheaper. Unfortunately, I've learned this too late. Okay. So, all right. So I'd like to define not Floer homology, and let me. It'll be based on what are called grid presentations for knots. So a grid diagram is the following object. We take an n by n collection of squares in the plane, and we're going to mark them with x's and o's with the following rule. Every column has exactly one o in it and exactly one x in it, and every row has exactly one o and one x in it. So here's an example. And the statement is that this representation gives rise to an oriented link. And the oriented link is represented as follows. You connect the O's and the X's vertically by a segment, and then you extend them, connect them horizontally also by segments, but with the understanding that the vertical segments are overcrossings and the horizontal ones are undercrossings. And in this way, you've always specified a link. And in fact, there's an orientation convention that the horizontally I go from the O to the X, and that gives us an orientation. So an oriented link is represented by this n by n block of squares marked with O's and X's, subject to those rules. Okay, is that clear? Okay. So this is going to be the manner in which we represent our links to define our invariant, and I'd like to pretend that the starting point is the following observation. So look at this picture. There's a and we're going to think about these as being lattice points. And what I'd like to do is I'd like to mark each lattice point with the winding number of the link around that point. So for instance, the winding number here is -1. Just write the matrix of winding numbers. And I'm going to think of that winding number as the exponent of a formal variable t. So here I put t inverse because the winding number of this point around this knot is -1. And I'm going to put a t inverse here, t inverse here, t inverse here, t inverse here. Here I put t to the 0 because the winding number is 0. Here I put t inverse again, and here I put t to the 0, t to the 0, here t to the 1, t to the 1, and so forth. We're going to take this matrix right here. And I'd like to make the following observation. The determinant of this matrix is equal to up to factors of t and sines, an overall sign, t minus 1 to the n minus 1, where n is this grid number, times the Alexander polynomial of the knot. So this is the observation on which I want to base our whole story. So you can verify this by looking at the Skane relation for the Alexander polynomial, for example. So what we would like to do is we would like to categorify this. Pardon?
Can you repeat the determinant?
The determinant of this matrix. So I'm going to have a matrix of monomials in T, where the exponent of the monomial is the winding number of that particular point of the knot projection around that point.
It's always square.
It's a square. So I'm going to look at this kind of n by n.
What you put the t's on the edges or on the vertices?
At each the corners. So remember, the knot is passing through kind of half integral entries, and my matrix I'm going to think of as living at integral lattice points. And at each integral lattice point, I look at the winding number of that point, of the knot around that point. And I'm not going to look I'm going to look at this n by n block and take its determinant. You could have said, why this one, why not this one, and you get the same answer. But so if we're going to look at this n by n block, we get the determinant of this kind of matrix of t powers is some multiple of the Alexander polynomial. Okay, so this is going to be our starting fact, and from this we would like a, if you like, a categorification of this statement. What we would like is a homology theory whose generators are the terms that you count in a determinant, right? You can think of a determinant as being just a count of permutations with a sign, which is the sign of the permutation, times a t power, which is telling you kind of where you're landing. And we would like a chain complex whose generators correspond to those permutations, and whose gradings are, well, one of its gradings is going to be just the sign of the permutation, at least mod 2. So we'd like a z lift of that mod 2 quantity, and we have to like to introduce a differential on that. Okay, so that's going to be our goal, and here's how we achieve that goal. So this picture took place on the plane, but I'd like to work on the torus. So so I'm going to think of the torus, and I'm now not drawing the x's and the o's, but think of the x's and o's as being there. So I'd like to have generators of my chain complex. The generators of my chain complex are going to be what we call grid states. A grid state is, if you like, a one-to-one correlation. So, okay, on the torus, if I've identified the left edge with the right edge and the top edge with the bottom edge, these horizontal segments become circles. So I have n horizontal circles and n vertical circles. And a generator, a grid state, is a one-to-one correspondence between the horizontal and vertical circles. If you like, it's just the graph of a permutation. So I'm going to have a grid state being an n-tuple of points where one point lives on each horizontal circle and one point lives on each vertical circle. And remember, working on the torus, so this point is the same as this point, and this point is the same as this point. So these are what we call grid states. Or X, I don't know. X grid states. No, X is bad. Math frac S are the grid states. And we can think of them as graphs of permutations. So what I would like to do is I'd like to define a chain complex, which I'm going to now call GC tilde of our grid diagram, which is just the the vector space generated by grid states. Let's work with Z2 coefficients, though we can work with Z coefficients with a little extra work. So we're going to have the vector space generated by these grid states. And now I'd like to introduce a differential on this. And the differential will be the following. So there's a, all right, so I'll define the differential before I define the gradings. So, no, I'll define the gradings before I define the differential. Okay, so this complex is going to come with two gradings. Pardon?
That's G with this.
This is the grid diagram. This is G. Yeah. Yeah. Now, okay, so what I would like to do is I'd like to define two gradings on this chain complex. And this is okay, so one grading is, we're going to call it the Maslov grading. And if you think about generators as being permutations, then the permutation has a sign, and what I'm going to do is I'm going to define a z lift of that sign. So there's a unique function n from grid states of the grid diagram into z. In fact, let me call this a proposition. There exists a unique function from grid states to z with the following two properties. The first is a normalization. I want this grading to for a particular grid state to be 0. And which particular grid state are we going to take? We're going to take the grid state that, if you remember, we have these O markings, and we're going to just look at the grid state that is the upper right corner of each O marked square. That's a particular grid state, which I'm going to call northwest of O's. Okay? That's a canonical grid state that you have on any grid diagram, and I want the grading of that to be 0. Northeast. Sorry. Northwest. Sorry. Any other question? Okay. And the second one is, I want this to change nice. And now I have to define something else. So pardon me. Let me backtrack a little bit. So we have to talk about rectangles. The differential is going to the differential in our chain complex, which I haven't yet defined, is going to count rectangles. And I have to talk about an orientation convention I have to talk about what I mean by rectangles. So if I have a grid state, which is this green grid state, then you can imagine another grid state, which is the same as this green grid state, except at exactly 2 points. And so I have this green grid state and this orange grid state. So two grid states differ by a rectangle if they're the same at all but 4 positions. Okay? And that's equivalent to, if you think about your green grid state as the graph of a permutation and the orange one as a graph of a different permutation, those two permutations differ by multiplication by a transposition. Okay? And now, if I've got two such grid states, there are actually 4 rectangles in the torus which have the property that their corners are the 4 points where these grid states are different. There's this rectangle, there's this rectangle, there's this rectangle, and there's this rectangle. Okay? So I want to now talk about an orientation convention. 2 of these rectangles I'm going to think of as going from the green grid state to the orange grid state, and 2 of them will be coming backwards. So if the rectangle is oriented so the rectangle inherits an orientation from the ambient torus, and if horizontally I'm going from green to orange with respect to the oriented boundary, then I'm going to think of that as a rectangle from green to orange. So for example, this goes from green to orange. And this one goes from orange to green. And this one goes from green to orange. And this one goes from orange to green. Okay? So there are two rectangles that go from green to orange and two that go from orange to green, always. Okay, so now I want to say how the M grading of the green and the orange grid state are different. And the statement is that the grading of of P minus the grading of Q is equal to 1 minus twice the number of times something happens. And that something is the number of O markings inside the rectangle. So that's something that I suppressed from this picture. But remember, in a grid diagram, we have these various O markings. And so here we're going to have minus twice the number of O markings. And let me just consult my notes so I don't get a sign wrong. Plus twice the number of times R, the interior of R contains a component of P. So this rectangle has no green-orange markings in its interior, but this one contains this green-orange point in its interior. So I want to add twice the number of green-orange markings. Oh, I'm sorry. For any rectangle that goes from P to Q. So I've got this function. Anytime I've got two grid states that differ by a rectangle, then the difference in their gradings is given by this formula. Okay? And the first thing you have to check is that this is not it's an overdetermined formula. You have to make sure you don't get into any contradictions. And the nicest way to do that is to actually write down a formula for that specifies this function.
I mean, I guess that you didn't just wake up in the morning and did this, right? So what's is really behind? What's the secret behind this?
Okay, so all right. Let me define the differential, and then we'll come back to the grading, and then maybe that'll give some inspiration for what the secret is. So we're going to define this is not a fair answer to your question. I'm going to give an unfair answer to your question. You're not going to get one. So the differential of P is going. So what's going to be the differential in our chain complex? It's going to count empty rectangles. So the differential of a grid state P is going to be a sum over all other grid states of a count of empty rectangles. So I want to look at the number of rectangles which have the property that R intersect O is empty, R intersect X is empty. So it has no X markings inside of it, no O markings inside of it, and no P markings inside of it. And that's going to be the coefficient of Q. So this is going to be our differential. And what I want to do is I want to define a grading that respects this, that's respected by this differential. And so if there is, so in a homology, in a chain complex, you expect there to be a grading that drops by 1 under a differential. And if there is such a grading, then it certainly should have the property that if R intersect O is 0 and int R intersect P is 0, then the grading of P should be 1 bigger than the grading of Q. So if you believe that this differential has a Z grading that drops by 1, then this formula should follow. And actually, those requirements are sufficient to uniquely determine M, because any two grid states can be connected by a sequence of rectangles in such a way that that at least there are no so that with the property that at least well, the property that these two things are 0, and that's an easy property of the fact that the group of transpositions that the symmetric group is generated by consecutive transpositions. Okay. All right. So that was the answer to that question. Okay. So I want to define now a second so anyway, that answered this, and the normalization convention is actually just done so that for the unknot, you want the homology theory to be graded in dimension 0. So that's the reason for that. Okay, so we have this function. Yeah? No, of course.
I mean, this is kind of the new theory that you have.
Yeah.
What it has to do with the what is it called?
Holomorphic disks?
The previous one you had with Zabrodsky.
So it's isomorphic to it.
So it's isomorphic.
It's isomorphic to
So
it.
it's just like a kind of a very different
It's a
presentation of.
It's actually not that very different as presentation. It's a different presentation. It's one that I can talk. I don't have to talk about holomorphic disks. When about holomorphic disks, the original definition used pseudo-holomorphic disks in its definition, and I had to talk about Lagrangian Floer homology. And here I'm going to give a definition that's combinatorial and completely self-contained. But it's actually
So in some sense, that's the right answer. That's the fair answer that you are kind of.
Yeah. Okay. That's right. That's right. That's right. That's right. That's right. Okay. Good. Okay. Good. Yeah. Yes. That's right. So this is a combinatorialization of the holomorphic theory. Okay. Any other questions?
There's no one said it right. There's no theorem that one can prove using this presentation that you didn't know with the other one.
There's no. There's Wait. Those are two different statements, right? One is about a theorem, and the other one's about insight. Yeah, there's no new theorems that you can prove using this construction. But actually, it was very helpful to build intuition about things. So, like in other contexts, it's very useful to think about grid diagrams. So I like them. But you can do computations in a way that you couldn't otherwise. Okay, great. All right, so now I wanted to define a different grading as well. So this grading, as you notice, it doesn't make any reference to where the X markings are. And so this function somehow depends only on the O markings. And so now we're going to define another grading, which is
Does M stand for Maslov?
yes, M stands for Maslov. And now I'm going to define something called an Alexander grading, which is just 1/2 the Maslov grading. I'm going to give this a better motivation in a moment. So it's 1/2 MO. So I could imagine defining the same grading with respect to the X markings. So now I'm going to take the difference of those, and I'm going to normalize it by n-1/2. And observe the following, which is not so hard to check. Says that the Alexander grading of P minus the Alexander grading of Q is the number of X markings inside of the rectangle minus the number of O markings inside of a rectangle whenever you have a rectangle from P to Q. So this is an easy consequence of this property over here, and it's a not very hard exercise in planar geometry to see that that this Alexander grading up to an overall additive constant is the same as that sum of winding numbers that I mentioned at the beginning of the talk. Yes?
There's two notions, right? That is grid thing, which is points on the intersections, and there is the O's and the X.
That's right.
So how do they connect?
So what happens is that when you specify the grid diagram, you specify at the beginning of the day the O and the X markings.
I specify, okay.
Yeah, and then we're going to have a chain complex whose generators are all the different ways of putting our grid states down.
With this O and X?
With that fixed O and X,
okay.
X fixed. And now we're going to write, now we have a differential which,
Yeah, okay.
okay. Okay, any other questions?
So the
Yes?
definition of the MO, you have used O twice for NWO and for
Yeah, that's right.
and for R intercept.
That's right,
Now
yeah.
you're going to switch both of them for X.
That's right, yeah. I switched both of them for X. That's right. Any other questions? Okay. So, great. So one thing is, so here are two kind of obvious things. One is the following proposition that that this differential drops M grading by 1. That's because we're only counting O-less, P-less rectangles. So it drops it by 1. And also it preserves the A grading, because all of our rectangles are also X-less. Okay? So what that tells you is that if, well, okay. And now, of course, I should say the most important property, which is that D squared equals 0. It's a chain complex. And, all right. All right, so here's the proof. So the proof is a combinatorial proof. Okay, so here's the proof. So what we have to do is we have to understand how two different rectangles can interact with each other. So for example, if I've got a term in D squared, what does that mean? That means I have a differential, some rectangle that goes from some P to some Q, and then another rectangle that goes from Q to some T, right? So, and how can that look? Well, it can look in several ways, but one way it could look is that I've got my rectangle that goes from P to Q, and then I have my second rectangle that goes from Q to T. Right? So I've got this, my grid state, this grid state P. I've got this grid state P. And it moves from P to Q over here. This stays fixed. That means that this vertex is both at P and at Q at the same moment. Then I go on from Q to T. And first, I've got my first rectangle R1, and I've got a second rectangle R2. And what I have to do is I have to find a second way of going from P to T that cancels that. Well, here's one way. I could take this rectangle first and then this rectangle. So that would give you an R1 prime, which is a different rectangle, which goes to a different Q prime. So what different Q prime is it? Well, it's one of its coordinates is going to be still here. So these rectangles, they come in, these rectangle juxtapositions come in canceling pairs. I've given you only one example of how two rectangles can interact. The other main way two rectangles can interact is they could simply be disjoint. I could have this rectangle R1 and then a different rectangle R2.
So where's R2 prime in this picture?
So where's R2 prime? It's this big rectangle right here. So so here's another picture where I've got R1 here and then R2 here. I can just do them in the other order. I can do this one first and then this one. And so again, we see canceling pairs. And there are other cases. This is just like this. So okay, so the D squared equals 0. And by the way, so this is an elementary argument. Not hard to write down all the details. It's a it's a sort of combinatorial variant of Gromov's compactness theorem for pseudo-holomorphic curves. So just like in Lagrangian Floer homology, Gromov's compactness theorem is the driving force that makes the whole theory work. The driving force that makes this theory work is this silly observation about rectangles. And that statement continues. So I'm going to prove lots of theorems that have to do with how polygons in the plane intersect and interact in this manner. Okay? So d squared equals 0, and we can take the homology of this chain complex. So the next observation is that, so it's a chain complex, it satisfies these properties. I'm going to write the chain complex. It splits as, I'm going to always write the Maslov grading as a subscript. And I'm going to write the Alexander grading as coming along over here. The subscript behaves the way you kind of remember the dimension of a homology theory behaves. And this term is like, it's like a direct sum of different chain complexes. So, okay, good. So, the thing is that when we take the homology of this chain complex with respect to this boundary operator, this is a bigraded vector space. So the Alexander and the Maslov gradings descend to this homology. Okay, good. So the next sad fact is that this homology group is not a knot invariant, but it's not far from being a knot invariant. So here's the statement. So let me start with the ungraded statement, which is that if you look at the full dimension of the grid homology group of a grid diagram and divide out by 2 to the n minus 1, where n is that grid number, this is always an integer, and this is a knot invariant.
Can I bother you?
Yes, please.
You do all this over Z mod 2Z.
I do.
Is it really essential?
No, it's not. So if I
Is it just because the plus minus orientation, like easier to do the?
Yeah, I mean, if I wanted to do a Z coefficients, I would have to explain how a rectangle gets a number which isn't plus or minus 1. So each rectangle is no longer going to count just plus 1. There are some rectangles that count plus 1 and some that count minus 1. And I would have to explain how that works. That's right. That's right. That's right. So that's right. That's right. That's right. It's a very nice story, but maybe it goes a little far out. Okay. Any other questions?
And these dimensions, the grading. I mean, let's take even fields.
Uh-huh.
Will be depends on the field. Some.
That's okay. So here's a remarkable fact. If you define this over Z, in every single known computation, the grid homology is a free Z module, which means that the homology looks like it's independent of P. But there's no conceptual reason why that should be true. So it seems that that's probably an artifact of the fact that we only see small knots. So maybe if you want a probabilistic problem for large knots, that could be another example. So that we don't know right now. For posterity, in all known cases, GH tilde of a grid diagram defined with Z coefficients, which I haven't done, but it can be done, is a free Z module. And the question is this really true? There's no conceptual reason that I know of to believe this to be true. So it's quite likely that someone should be able to find some Z mod P's for which there are different ranks, but we haven't done that yet. Okay, good. Any other questions? Okay, so all right, so let me, this is annoying, right? So this is not a non-invariant. You have to divide out the dimension by something. But let me give a more precise statement and then a better definition. So the more precise statement is the following theorem, which is that the grid homology of a grid diagram is isomorphic to a different grid homology, which is now the invariant that I talked about last time that's really a not invariant, tensored with a two-dimensional vector space raised to the n minus first power. And here W is a two-dimensional vector space with one generator in bigrading 0, 0, and another generator in bigrading -1, -1. So what this means is that, and this is a non-invariant. And so then this is an obvious consequence. But let me give you now the definition of this non-invariant. So this involves a little bit more algebra than what we've talked about. And we have to count more rectangles to make that definition. So what I'd like to do is I'd like to define an even more general grid complex, which is a module over Z mod 2 adjoin n formal variables. And it's going to be a free module generated by the grid states. Unfortunately, I erased my earlier differential, but here's the definition of this differential. The differential of a grid state P is going to be a sum over all grid states Q of a sum over all rectangles from P to Q. And I, again, want my rectangles to contain no points of P in their interior. And I also want them to contain no X markings. But I do allow O markings. And I'm going to think of my O markings. In order to make this definition, we have to label all the O markings from 1 to n. And if my rectangle contains O1 and O7, then I want to say that the rectangle contributes the monomial U1 times U7. Okay, so I'm going to U1 times the number of times O1 appears in the rectangle times the number UN times the number of times ON appears in the rectangle, and that's going to be the coefficient of Q. So this is the bigger, fatter differential, and you're supposed to observe.
The numbers.
Say again? Yeah, these are sort of the number of times this occurs, and of course this number is always 0 or 1. And what else do I want to say? The differential, okay, so I have to talk about how multiplication by U behaves with respect to the gradings. I had an M grading and an A grading, and what we want now to say is that UI drops the M grading by 2 and the A grading by 1. That might look unnatural at very first glance. You know, when you take homology with coefficients in some other ring, then usually you think of the ring as preserving the degrees. But then when you think about, for example, S1 equivariant cohomology, you have an action by a polynomial algebra which drops the grading by 2. So it's actually not so unnatural from the perspective of other parts of mathematics. And these are also the conventions that you need in order for the differential to drop M grading by 1 and preserve the A grading. So So these are the properties. So now this is the homology of this complex is a module over f of u1 up to un. And you're immediately supposed to say, well, then how on earth can it possibly be independent of n? But the answer is the following, that here's a lemma. Multiplication by ui is chain homotopic to multiplication by uj for all I and j. So somehow, like, it's a module over u1 up to un, but really you can think of it as a module over any of the ui's that you like. So it's really just a module over f of u. And what's the proof? The proof is Gromov's compactness theorem. So we have to define a homotopy operator that satisfies boundary h plus h boundary is equal to u1, ui minus uj. Now, let's not define that in general, but let's assume that OI and OJ have the property that there is a single X that lives in the same row as OI and in the same column as OJ. And we're going to construct a homotopy between multiplication by UI and multiplication by UJ. And that homotopy operator counts rectangles. Remember, our differential counted rectangles that have no x's inside of them. Our homotopy operator is going to count rectangles that contain exactly that x. So, so I could write this formula again. I would change this to h, and I would say R intersect x is equal to xij, that one xij. So I won't write it again, okay? And what you're supposed to observe is that this relation holds. And what's the proof? Well, we look at how rectangles can interact with the rectangle that has our fixed x. Rectangles that have no x markings in them can interact with that rectangle that has that particular x marking in them. And again, I might have this rectangle juxtaposed with this rectangle, or alternatively I have this rectangle juxtaposed with that rectangle. And those are canceling terms of boundary h and h boundary, or boundary h and boundary h, depending on the exact geometry. And now you're supposed to tell me, what about ui minus uj? And ui minus uj occurs because there's a very special way two rectangles can interact that I didn't talk about earlier, which is that I could have a rectangle and then follow that by a rectangle that goes all the way around the torus. And two observations. If I have this juxtaposition of two rectangles, then its width has to be 1, because otherwise it would have some, PQ point in its, one of the rectangles would have a PQ point in its interior. So the width of one of these rectangles has to be 1. And moreover, there's always, for any column, there is such a pair of rectangles, because in any column, I have my initial generator. It looks like some p here and some p there. I can always find a rectangle, a thin rectangle, that takes me away from this p and goes to this q. And then I can just take the other rectangle that goes from the q back to that p again. So any thin column can be decomposed uniquely as a juxtaposition of two rectangles like this. You might have said, why didn't I discuss that earlier when I said d squared, when I talked about the d squared equals 0 proof? Well, there we had the luxury of never looking at rectangles with an x marking inside of them. So we didn't have to look at juxtapositions at these thin annuli. But in this story, we do have to look at that particular column that contains that particular xij. And in the same, and what does that contribute? Well, that contributes multiplication by uj. And there's also this particular row, and that contributes ui, and that's the reason for this formula. Okay? Is that clear?
Yeah, but how it relates to the compactness?
Oh, I'm sorry. So whenever I talk about this, I mean, I think of this as a combinatorial analog of Gromov's compactness theorem. This statement that that we look at two different that these moduli spaces cancel in pairs, and if okay, so that's not just poetic. There's actually a geometric way of thinking about this. There's really a moduli space of holomorphic disks inside of a second symmetric product of the torus. And there's a moduli space of disks which has a cut going on, and one end is this juxtaposition of rectangles and the other one is that juxtaposition of rectangles. So there's actually a literal connection to Gromov's compactness theorem. But what's nice here is that we don't actually have to think about it that way. We can just think about it combinatorially. Okay, any other questions? Okay, so we now have this chain complex, and there are there's another thing we can naturally do to that chain complex, and that is we could set U1 equal to 0 in that chain complex. I've just defined this chain complex GC minus. There's another chain complex GC hat of G, which is just GC minus of G modulo U1 times GC minus of G. Another way of saying that is that you look at those rectangles that don't contain O1, and you count those. And that seems to pick out a rectangle, but basically this lemma tells you that it doesn't depend on which rectangle you picked out. So the theorem is that GC hat of G and GC minus of G are not invariants. And the relationship with GC tilde of G is that if you take this GC minus of G and you set U1 equal to 0 and U2 equal to 0 and UN equal to 0, then you get the chain complex I started with, GC tilde of G. Say again? Okay, so the original proof was that, well, this agrees with the holomorphic theory, so it's a non-invariant. But a better proof, but there is a combinatorial proof, and I want to sketch that. What's that?
This invariant knows about the action of the FU, or
Yeah. So what I should say is that this is a module over f of u. It's a graded module over f of u, and this is just a vector space. Since I've set U1 equal to 0, somehow all the u's act trivially in homology. So this is sort of a stupid f of u invariant. This is an f module, or a vector space. And this is a module structure on it, and we're going to use the module structure to actually prove a theorem at some point. Okay? Are there any questions before I sketch the proof?
So GC is chains and GH is homology.
Yeah.
The chains are invariant then?
Sorry. Thank you. Any other questions? This is okay. No, this is correct. Okay. Any other questions? Okay. So, all right. So now, why is this a non-invariant? So So the first proof was from our paper with Sarkar from 2006, and I'm going to describe the combinatorial proof, which is from 2006 as well, I think. I don't remember exactly. Okay, and this is also chapter 5 of our book. Okay, so so how do you prove that it's a non-invariant? So the basic point is that, well, grid diagrams actually have a long and distinguished history. They go back to work of Brunn from 1898, and they've been repeatedly discovered in mathematics. They're equivalent to the presentations of knots that were studied by Berman and Manolescu, and they were studied very nicely by Dinikov and Cromwell. And Cromwell actually formulated a theorem which says that that if you attach something, okay, so let me say a few words of background before I state this theorem. I'm not really going to win any awards for Blackboard technique, am I? Oh well. So let me tell you some moves that don't change the knot type, but change a grid diagram. If I've got a grid diagram, and suppose I've got two consecutive columns, and suppose that the O and X markings of one of the columns does not kind of interleave the O and the X markings of the other column. So this is allowed, this is not. In this case, I can just take these two columns, I can switch them, I can commute them, and that's called a commutation move. And it's not hard to see that that actually doesn't change the knot type. So it might actually do nothing at all. In more exciting cases, it might be a Reidemeister 2 move, right? But these commutation moves don't change the knot type. And there's another move that doesn't change the knot type, which you can think of very sort of, if you think of a grid diagram as really some kind of representation of the knot with by sticks, then you can just take one of the sticks and put a notch in it. That's a stabilization move. And if I want to actually say it from the point of view of grid diagrams, it's a little bit more of a mouthful. But let me just do that anyway. So suppose that you have a 2x2 block in your grid diagram with the property that 3 of the squares is marked. So maybe I've got 2 X's and an O, and the fourth one is left empty. Then I can do the following game. I just erase this horizontal circle and this vertical circle, and see what's left over. So this, I have an O over here. Now that O belongs to that bigger square. And right at this 2x2 block, we're a democracy. So what happens is we vote. And there are 2 O's. So we're going to mark this guy. It's 2 X's, so we mark the big guy with an X. And that way, we've just constructed a smaller grid diagram. That's called a destabilization. OK, is that clear enough? So let me just draw that one more time. Pardon? Yeah, I have an O here, and I've got an O here. And what I do is I just put the O here, the X here, and the O here. And leave everything else the same. Okay? Okay, so this is a destabilization. This is stabilization. Okay, so Cromwell's theorem says that if you've got 2 different grid diagrams for the same knot, then you can always connect them by a sequence of commutation moves, stabilizations, and destabilizations. So if you have something that's invariant under those moves, then it's in fact a knot invariant. So any 2 grid diagrams for the same knot can be connected by commutation moves. Yeah, so there's a very nice exposition of this by Dinikov, and the way he does it is he shows that he explicitly expresses those moves in terms of Reidemeister moves, sequences of Reidemeister moves. Cromwell's proof uses Markov moves. But
the opposite also, that every Reidemeister move can be expressed as
that's right. So you have to check that. That's right. We also have a proof in Appendix B of our book. Okay. All right. So all right. So now we just have to check that the chain complexes are invariant under these moves, and we have to check to see how long we have to do that. beautifully in time. And let me start with the nicer proof. Okay, so let's imagine trying to prove that the grid diagrams are invariant under a commutation move like this. So it's going to be useful to draw both grid diagrams on the same picture in the following sense. So I want to think of that I've got an O and an X and an O and an X. And I can draw, instead of drawing vertical straight circles, I'm going to draw a vertical wavy circle. So here's a green vertical wavy circle. Here's an orange vertical wavy circle. And if I ignored the orange wavy circle and straightened out the green one, I would have this diagram. And if I did the other one, then I would have this diagram. So this is somehow the green diagram. And this is somehow the orange diagram. And what I'd like to do is I'd like to define a map from the green complex to the orange complex. So these are two different grid diagrams. There's a green grid diagram and an orange. Is this too evil for anyone trying to take notes? Okay, good. Nobody said anything. So I've got my green grid diagram and I've got my orange grid diagram. And I would like to define isomorphisms between their grid homology groups. So before defining an isomorphism between two homology groups, it's nice to have a chain map from one to the other. So I'd like to define a chain map. And my chain map is going to count pentagons in the following sense. So I'm going to just draw that picture again bigger. So my grid diagrams look like my sort of big composite grid diagram looks something like this. And I can look at pentagons, which have one corner at, so there are two intersection points between the green wavy circle and the orange wavy circle. Let's call them C, and we're not even going to give the other one a name right now. So I'm going to look at pentagons, which have one corner at C, and the other four corners somewhere else. So, for instance, they might have corners at some grid state P and other corners at some other grid state Q. P in this case is going to be a grid state for the green diagram, and Q is a grid state for the orange diagram. So these pentagons give you a way to connect from green grid states to orange grid states. And I'm going to define a map now from the green complex. So this is, now I have to pay for from the green complex to the orange complex. And you're going to notice that I'm going to go very lazy with writing down definitions of maps. This is a count of pentagons with this property. And when I mean by count of pentagons, I mean I'm not going to count pentagons that have any green-orange points in their interior. I don't want to count those. I'm not going to count any ones that have X markings in their interiors. And if they have O markings in their interiors, that's okay, but I count them with a U power, just as before in the differential.
GC minus.
The GC minus, yeah. Yeah, I'm defining it on the level of GC minus, and you can specialize to all the other versions if you like. Okay, is that clear enough? And now the statement is that F is a chain map. What's the proof? Okay, so the proof has to do with how a pentagon and a rectangle can interact. So Again, a pentagon and a rectangle can decompose as a rectangle and a pentagon. So we have the statement is that boundary f plus f boundary is equal to 0. And the slightly entertaining point is that it's not always the case that terms in boundary f cancel with terms in f boundary. They might cancel in the same place. Like, for example, I think, if I remember correctly, this is going to be an example where the rectangle comes first and the pentagon comes first, or the rectangle comes first. Sorry, the rectangle comes first and the pentagon second, or the rectangle first and the pentagon second. So those are two terms here that cancel. But at any rate, geometrically you get the same cancellations of pairs. Okay? Any other questions? Any questions?
Instead of the field vector characteristic node 2, you do the same with sign.
Yeah, that's right. That's right. That's right. Excellent. So, and of course, we have a map the other direction gotten by counting not pentagons based here, but pentagons based at this point. So here, the initial point with our orientation convention is orange, and the terminal one is green. Okay? So the point C gives us maps from green to orange, and the point C prime gives us from orange to green. Okay? All right. So we have chain maps in the two directions. Why do they induce isomorphisms in homology? It's all like in our first course in algebraic topology, when you show that, homotopy equivalent spaces have isomorphic homology groups, you construct homotopy operators. So what we need is a homotopy operator, an operator that gives you homotopy between, I need better names. Let's call this F and let's call this G. What we have to show is that G composed with F is homotopic to the identity map. Chain homotopic to the identity map. Okay, so what's going to give us a chain homotopy? What geometric things could possibly give a chain homotopy? Hexagons, of course, right? So you could count hexagons. That's a green hexagon. That's a green hexagon. And you can define a map H from green GC minus to green GC minus, which just counts hexagons, meaning that I don't count hexagons if they have X's in them or P's in their interior. And if I've got O's in them, then I pick up U powers. So that's going to be the operator, and we have to check that boundary H plus H boundary is equal to the identity map. No, F composed with G. G composed with F? G composed with F. Minus the identity map. Plus minus the identity map. Working mod 2, who cares? Okay? How do we see that? Well, again, it's the usual thing. We see how a hexagon and a pentagon can interact. So in this case, I have a hexagon. This is the term in H followed by boundary. H followed by boundary. And the alternative decomposition gives us a point in F composed with G. Right? And now you have to worry about where the identity map comes from. And the identity map comes from looking very locally in this thin column. In the thin column, there's here's a so here's a term in here's a very thin pentagon that contributes to F, and here's a very thin pentagon that contributes to G, and it takes me from this green grid state back to itself. And you have to check that there isn't anything else, but that's the point. So that that F and G are homotopy inverses to each other, so they induce isomorphism and homology. Okay, let me just check to see how I'm standing at the time. Great. Okay, so we're halfway there. We have to now check that grid homology is invariant under stabilization. And any questions? Okay. This is a slightly funny thing because now, if you, oh, am I off? Oh dear, I was, sorry, I was somehow thinking 5:30 instead of 5. I guess I must be done. Okay, so then there's a stabilization proof, and sorry, gee, you all have been very polite. Okay, so that's half of why not Floer homology is an invariant, and I'll have to continue next time.
Okay, so let's thank Peter for this. Are there any questions?
Yeah?
So is there a way to use the modular polygons to define like higher, like infinity structures on these chain complexes?
Yes. But I don't see how you're going to get something. Well, I don't know how to get something interesting and exciting from that point of view.
No extra.
Yeah, I don't think how you get an extra. What's that?
Is there no massey products or anything like that?
So, I don't know how to do anything exciting that way. Now, maybe that's just a problem with my lack of imagination. So I can. I can interpret your question as follows: that. Okay, no, let me stick to that answer, and maybe we can talk about it later some more. Yes?
How many groups you have in a chain complex?
How many whats?
In this GC is a chain complex.
Yeah.
A lot of groups and maps between them. So how long is the chain? You have just two groups and this one?
I'm sorry, these were two different chain complexes. There's this one and this
No,
one.
I mean just stick to one of them.
Stick to one of them. Oh,
Then you have this D map.
I had a D map. I have a differential.
Yeah, this differential.
Yeah?
So you have just two groups and one differential between them? Or
No, I have, you're supposed to think of it this way. Yeah, I have GC DS, and I have a differential that goes from GC D minus 1 GS. And the way, a priori, you know, there are infinitely many of these indexed by S's and infinitely many of these, but in actual fact, there are some bounds because it's finally generated as an f of u module. So, if S is sufficiently large, then these groups are just trivial.
Last time you showed that there is some symmetry in the homologies.
Mm-hmm.
Is it realized by some kind of duality map, or is that?
So it depends on which symmetry. There's some symmetry that's realized by the fact that there's some geometry of the grid diagram you can reflect in this way, and that gives you one of the symmetries. And there's another symmetry that's gotten, I think, by reflection this way.
Just a question. When you were drawing these connotation loops, like, why do the X's and O's, why can't they be intertwined?
Oh, if the X's and the O's are intertwined, then that corresponds to a crossing change operation. So, like, if I take this knot and then I take this knot, I've just introduced a crossing.
There's the over and under thing.
That's right. And in fact, that's very important. That's a very important observation. So If we were to prove the Milnor conjecture, we would use this fact.
So it's true that you get a map induced.
Yeah.
A map induced by that process.
That's right. That's right. That's right. That's right.
Yeah, I know.
Okay.
Is the U, maybe it's shorter, the U variable action reflects some sort of S1 action on the...
Yeah, I mean,
hinted at that, but
yes, that's right.
about it?
So I don't have a rigorous answer to that question, but Seiberg-Witten-Floer homology is constructed as an S1 equivariant cohomology theory, and Heegaard-Floer homology is isomorphic to Seiberg-Witten-Floer homology, and it's a module over f of u because of this reason. So somehow the isomorphism is with an a priori S1 equivariant theory with this other theory that defines a polynomial algebra over as a chain complex over a polynomial algebra. I don't know how to see the S1 action from this perspective. I'd be very interested to see that if anyone could give me some insight. I wonder if you have a chain complex over, if you have a chain complex over Z of U, is that somehow naturally the equivariant complex of some space with of an S1 equivariant space or something like that? I don't know. Yeah.
Does it look like a Seiberg-Witten version of all this not homology business?
So actually, annoyingly enough, there's no Seiberg-Witten version of exactly this question. There's no Seiberg-Witten theory for a closed three-manifold is an S1 equivariant cohomology theory, but the version for knots is not, at least not with its current definition. So Kronheim and Mrvka gave a definition, but that only captures the hat theory. It doesn't capture the minus theory. So no. But that might be just, again, some shortcoming of ours, not of mathematics.
Questions? Let's thank Peter again.